Vale, no estaré por aquí y un momento.
La introducción sin nada
Good morning, everybody. Welcome to today's special DIP seminar. It's my great pleasure to introduce Professor Solovej from the University of Copenhagen. We briefly introduce him to those who couldn't make it to yesterday evening's talk that he gave in San Telmo. He's a mathematical physicist who obtained his PhD at the University of Princeton, then started his career with postdocs and professor positions in the United States and Canada, and returned to Europe in 1995 to Denmark and became professor at the University of Copenhagen in 1997, where he is developing his career ever since. And in 2016, he was founding, or since 2016, he's a founding director of the Willum Center for Excellence in Mathematics of Quantum Theory. And he made a lot of fundamental contributions to our understanding of matter and the influence of quantum physics on matter, both bosonic and fermionic matter. And I think in today's, and he has received various recognitions for his work, among them the Poincaré Prize and membership in various scientific academies, like Royal Danish Academy and the American Mathematical Society. And in today's talk will show us how these bosonic and fermionic properties structure the periodic system. I feel I'm looking forward to your talk. Come, please.
Yes, it's a great pleasure to be here. And I just realized that my title is maybe a little presumptuous, saying that this is the mathematics of the periodic table. I should probably say that it is some mathematics of the periodic table. There's probably a lot more than what I'm talking about. That's a picture of the University of Copenhagen, the main building of the university. So we also have a very beautiful building. And right there, covered by my thing, is a statue of Niels Bohr. I covered it. I didn't cover it. Those that designed it. Anyway, so this is joint work with August Bjerg, who was a PhD student, or defending in a few weeks. And Søren Fournais was a PhD student 20 years ago, and Peter Hearnshaw is a postdoc. Okay, so I will tell you, this is the outline. I will tell you what I'm trying to say about the periodic table. I would like to understand the periodic table from a mathematical point of view, if I can understand the structure of the periodic table and explain it. So the way the periodic table is structured or built is the Aufbau Principle that tells us how the atoms are divided into groups in the periodic table, or it's a phenomenological rule for how it's done. So I'll describe that rule, and I'll see it's a challenge to try to prove it. And I will try to argue that we cannot prove it because it's in general would actually be wrong. And so I'll explain this. So I will look at different models of the atom. There's the full quantum many-body description. I'm doing non-relativistic quantum mechanics. It is known that there are exceptions to the Aufbau principle due to relativistic effects. I will ignore relativistic effects here, and that's not entirely true for large atoms, but that's what I'm doing. I'm looking at the non-relativistic many-body quantum description. So that's the most complicated model. Then there's a very simple model mathematically simpler, but that's the Thomas Fermi theory. I'll describe it. Particularly, there's the mean field potential in Thomas Fermi theory, and it leads to another model, usually not called the Thomas Fermi model, but I've called it the Thomas Fermi mean field model, and I'll explain it. And I'll remind you of angular momentum decompositions. That's important for the structure of the periodic table. Right? We know that the elements, that the orbitals are classified according to angular momentum, SPDF, whether the angular momentum is 0, 1, 2, or 3. I mean, in the naturally occurring periodic table, the atoms in the periodic table, we only see S, P, D, and F, L equals 0, 1, 2, and 3, but if we could make it bigger, it would go 4, 5, 6, 7, and so on. And that's what I will do. I will actually look at the periodic table if it was much bigger than just having the first 100 elements. And then I'll explain why, when I do this, the Aufbau principle would actually eventually fail. And then I'll go a little bit more into the mathematics. I will define these. When you do the angular momentum decomposition, you get one-dimensional operators in the radial variable. And I will study these operators in particular for the infinite atom. I will actually try to make the periodic table so big that there would even be an infinite atom. And I would ask whether I can see the periodicity if I go to that extreme limit of an infinite atom. That may sound crazy to you, but I hope to convince you that it's at least mathematically a fun game to play and that it may actually tell us something about the atom. And I will show that in this Thomas Fermi mean field model, the structure of the infinite atom is actually periodic, exactly periodic structure. But that requires they understand these half-line operators. And I will then give you the main result on periodicity. I will not give you the proof. I'll give you a very short sketch of the proof, which relies on WKB. So there's some WKB type matching. And then I'll conclude with what one would like to do in the future, or what I have done and what one would like to do. Okay, so now it again doesn't work. Oops, there it goes. Just very slow, that's the problem. I have to go back. Or what? Let me just use this. So there it is, the periodic table as you know it. I noticed there was also on the building out here. That's not the way I like to draw the periodic table, but it's the way you usually see it. I will have another version in a moment. So what is it? Just remind you, what is it that it tells us? It tells us that as we go down the groups, the columns in the table, the elements have very much the same chemical properties, right? I mean, out here we have the noble gases, and they react very slowly because they have filled shells. Here, for the alkali, we have the filled shell, and we've added one more electron, so they have one valence electron, and that's, of course, extremely important for their chemistry. The colors correspond to the angular momentums that we are filling. So for these red ones, we are just starting again to fill an S electron, so L equals 0. The yellow is L equal to 1. These are the P, L equal to 2, the D, and then the Fs, the L equal to 3. Okay. So the question I want to ask, well, we can understand this sort of periodicity. There's not really periodicity, but I try to explain how what the periodicity is, expected periodicity is, and what we can actually show. Now, one way to illustrate this, that they have very much the same chemical properties. This is just something I just did myself. I just said, let's find out what is the mass density, or here it's actually the average interparticle distance, so not the mass density, but really the particle number density, when we have the different groups. So here you cannot read it, but this is group 1, group 2, and group 13. So 1, 2, and 13. I just picked those. And then as I go down here, I calculate how many particles do we have per volume in the solid phase of these elements. And you see that it converges quite nicely in each of these two different values. Right? So for large Z, even for the Z's that we see naturally, we see some convergence to something that may look periodic, right? We go through different particle number density and then we come back. So that's what I'll try to explain. But to make it a real mathematical question, I will ask what happens as I let Z go to infinity. And this is then where chemists or physicists may say, wait a second, that's not interesting because there are only, well, here we go up to 118. So I think 118 is the last one that has been seen artificially. I want to go to much higher. And I don't want to do relativistic atoms, although I should when they get so big. I want to understand whether I can see this structure, which is for that we see at low Z, whether the full quantum problem, which I can study for large Z. The reason we don't see larger Z atoms is because of the instability of the nucleus. At least the reason we don't see it in a non-relativistic theory. I can go to arbitrarily large Z if I just think of the nucleus being finite. I can study the Schrödinger operator for very large atomic number, 5,000, 8,000, you name it. I cannot do that relativistically. Relativistically, independently of the instability of the nucleus, the atom will become unstable at 137, 1 over the fine structure constant. So relativistically, there will be instability at some point. But that's not what I'm worried about. I want to understand the non-relativistic atom, turning it into a math question, letting Z go to infinity, and see if the structure that we see can be understood qualitatively, maybe even with some estimates that are quantitatively interesting for the naturally occurring atoms. Then we get to the Aufbau principle, the way the atom is built up. I mean, how do we predict which elements are in the different groups? Now, I then drew the periodic table, not me, I picked this from the internet, from the what's called Web Elements, nice site on the periodic table. This is called the Janet periodic table. I mean, it's the same periodic table, it's just drawn in a different way. And it tells us how we fill in when we are in the different groups. When do we start a new group? So the rule in this is that you fill in a row, you start. So here, hydrogen, helium, lithium, beryllium. So you fill in like this, like this, like this. Then you go here, fill up, and then you go there, you fill up. Then you go here, you fill up, go there, and you fill up, and you go here. And the interesting thing is as you come down to a certain row, this is usually what's called the quantum number n, then you fill up the high angular momentum before you start filling up the lower angular momentum. Right? This is L equals 3, L equals 2, L equals 1, L equals 0, and then you continue. And this structure you can in principle continue. Right? If you want to prove that this is the right way of filling in the periodic table as Z goes to infinity, we know what to do. Right? I mean, every time you have a new L that you fill up 2 rows. When you have done 2 rows, you start the next L. So actually, we are almost, well, this is actually 100 and I think this is 120. We haven't really found this atom yet. But we would now, with 121, we would start filling up an L equals to 4, S, P, D, F, G, which would be down here. And then we would fill up the 4, the 3, the 2, the 1, and the 0, and then we would keep going. So this is the structure. This is the Aufbau principle. And I asked myself whether one could explain this mathematically. Can we really understand from the Schrödinger equation that this is what happens? Of course, you can calculate it for these elements and see that that's right, that the way the orbitals are filled in is according to that. But maybe it's just a coincidence that it fits with this structure because we are only going up to L equal to 3. Maybe if we continued, it would not continue like that. Or maybe it will. if it will, then that would be nice. We could explain it. So I asked myself that question, whether we can explain that this is the structure, and the answer is no. You cannot explain it, not because we're not good enough, because it's wrong. It would not continue like that. And I can prove this, and I'll give you the proof that if we really did larger and larger Z, this way of going 2 down, starting a new one, 2 down, starting a new one, would fail at something. Okay, now what about this thing of going to very large Z, Z going to infinity? Of course, there are no atoms that are larger than Z equal. Naturally, Z equal 92, I guess uranium is the last fairly stable atom. Nevertheless, it might be interesting to do this analysis of large Z, try to understand the mathematics, and then you may even try to do it in a quantitative way that will allow you to say something for the fine atoms. And somehow, some of the research I had done for large Z convinced the chemists also to do some of these calculations. I'm not sure that they were interested in understanding large atoms. They were interested in testing their calculational methods. So they were doing density functional theory, and they actually took Z going to infinity. Of course, what does Z going to infinity mean? They tried to tweak the density functional theories, and they went up to Z almost 3,000. And then they calculated the structure of the atom. What they calculated precisely was the ionization energy to see if there was still periodicity. And they used different density functional theories. And actually the authors, Konstantin Snyder, Perdue, and Bjerg, are actually the authors of one of the most famous density functional theories, the PBE, Perdue, Bjerg, and Insenhofer density functional theory. I mean, Kieran Bjerg told me that this paper he wrote on that density functional theory used to get at least 30,000 citations a year. So that's, I think, more than I'll ever have in my career. And also he says it has no effect on his H index, right? Because it's just one paper that's getting 30,000 citations. Anyway, this is one of the theories they did. So here are the groups they looked at. They looked at groups 1, 2, 3, and up to 8. They let Z go to infinity, and they calculated the ionization energy, and they found that it converges. It converges in the different group, but to different values. And then you would come back. So they somehow see this convergence in the density function. What surprises me a little bit, and I haven't quite found the solution to it, is that how did they define the groups? They defined it according to the Aufbau Principle, which I know is wrong. So it's interesting that they still got convergence. Maybe, so when I prove that it's wrong, it's for very large Z. Maybe Z equal to 3,000 is still not very large, but I have to somehow figure out why. So I have to talk to them about how it seems that it converges in there. Okay, so let me briefly remind you of the quantum physics of an atom. So this is the Schrödinger atom of n electrons, and you have Z. So I will always be looking at neutral atoms. So n will be Z, right? So we have n electrons. Kinetic energy is minus the Laplacian. I'm using units in which h bar is twice the mass of the electron. Otherwise, normally one would have a 1/2 here if you use atomic units. In atomic units, we have m equal to 1. And I would have preferred to use atomic units, but my student who wrote some of this used these units, and it was too much of a headache to recalculate. So I apologize that I'm using these units. So this is without the 1/2. Attraction to the nucleus, nuclear charge Z, E was set equal to 1, electron-electron repulsion. And this Hamiltonian acts in square integrable functions that are antisymmetric. Of course, for mathematicians, there's the issue of what exactly is the domain, but this is not a difficult issue at all. This is defined on functions in the second Sobolev space, and then it's a self-adjoint operator. There's a nice theory, and one makes perfect sense, and we can calculate the eigenvalue. I'm interested only in the ground state energy, which is the smallest point in the spectrum, so the infimum of all the expectation values when I normalize over psi's that are antisymmetric. Now, if I look at the neutral case, if n is too big, then there will not be a minimizer here because some electrons are going to fly out to infinity. But if n is, for the neutral case, there is a minimizer for this problem. This is known. And if I have such a minimizer, I can calculate the one particle density matrix. I'm writing it here in terms of its kernel, so it's a function of x and y. But you can also think of it as an operator, and this is the integral kernel for that operator. So it's what you get by doing psi bar and integrating out all the spin variables and all the space variables from 2 and up to n. And then for normalization, you multiply by n in here. Now, I don't know if you can see it all the way down there. That is the density. That's what you get when you plug in the diagonal. So the density of electrons per volume, is the diagonal, the XX of the one particle. And that's sort of what I'm interested in, analyzing for the ground state of that many body. So that's really complicated. We cannot say all that much about that fully quantum description. We can say much more if we do simpler models, and in particular, a density functional model, the simplest of them all. So this is the simplest model of an atom. Still a model of an atom. It describes the atom only in terms of its density. So it's the Thomas Fermi theory, and it gives us an energy only as function of density. So it's not another way of writing the theory I had for the full quantum theory. It's at best an approximation. But the energy as a function of density has an integral that you may recognize as the free Fermi gas, rho to the 5/3. While the attraction to the nucleus really only depends on the density, so it's z over x, rho of x. Electron-electron repulsion, well, this is what's called the direct form, where you do the density. So you think of the density of electrons as being a continuous, classical, continuous charge distribution, and you look at its Coulomb self-energy. Now, this is not the correct expectation value of the electron-electron repulsion in quantum mechanics. In fact, there's probably an expansion of some kind. There are corrections, and these corrections are usually called exchange corrections, exchange correlation corrections. I'm ignoring it here in Thomas Fermi theory. So this is the model in Thomas Fermi theory. Let me just remind you of where does the rho 5/3 come from. It's a semi-classical integral. You do the phase space integral, where you say you're filling up all the level up to some Fermi, or all the momenta up to some Fermi level F. And you determine F so that the volume in phase space, the 2 is because of the spin. The volume in phase space then will give you, not in phase space, but only in the momentum part. So you do it per particle. That gives you a function of x. This is the density. So you determine F, the relation between F and rho. Then you plug that into this integral, and then you end up with that expression there as a function of x. And then when you integrate over x, you get the energy. So this is a semi-classical expression for the energy, or what mathematicians like to call the microlocal expression. So that is a very, very nice form of very simple, depends only on one function of 3 variables. And you can analyze its minimum, just as I did before. So you now, n need not even be an integer now. You just say integral of rho is some number n, and then you minimize, and that gives you the ground state energy in the Thomas Fermi approximation. And I denote this will have a minimizer again if n is z, the neutral atom. It will have no minimizers if n is greater than z, but I don't care. I'm only looking at neutral atom. And the minimizer I call rho TFZ, Thomas Fermi for the atoms. And then let me say something about how good an approximation it is. maybe that's also a little difficult for you to read down here. So this is the quantum, the true quantum energy, ZZ, for the neutral atom. That is essentially what you get from Thomas Fermi theory when you minimize it. Except there is a correction that you can calculate, which is 1/4 Z squared. That's called the Scott correction. Comes from the innermost electrons. And this can be shown that this is correct. And if you add this in, you get something which is an error that's lower order than the Z squared when Z goes to infinity. I should say that the leading term, the Thomas Fermi term, goes like Z 7/3. So that's the leading term in the energy if Z goes to infinity. The correction is Z. So Z, it goes in powers of Z to the 1/3. So Z 7/3, Z squared, Z 5/3, and then we don't know anymore. We also know the Z 5/3. This is the Z 5/3 is a large piece of work done by Pfefferman and Secco about 30 years ago. But I didn't include that here. I only went up to the Scott corrected version. And so Scott predicted this in 52. Lieb and Simon proved the leading term. Hughes was a student of Pfefferman. Siedentop and Weikart then proved also together, these three papers proved this Z squared with a correction that's little over Z. Okay, let me go to the Thomas Fermi potential, because let's believe in Thomas Fermi theory. So then we have a Thomas Fermi potential, and then I can ask for the electrical field that the Thomas Fermi potential generates. I mean, the electrical potential, I should say. So this is the electric potential of the Thomas Fermi density field. This is the nuclear potential. And this total thing as a function of x is what one electron sees from all the other electrons, but also from itself, actually. You're counting self-energy. So this is the mean field potential. And there is an exact scaling in Thomas Fermi theory. So one can easily see that there's a scaling that if you change the density by changing the position by Z 1/3 and multiplying by Z squared, then it's the same as having the non-scaled and the Z 7/3. That's where this Z 7/3 leading correction in Thomas Fermi theory comes from. So the Thomas Fermi density, the minimizing Thomas Fermi density, has this scaling, a function independent of Z, and then this scaling. So in fact, the way to interpret this is that the atom shrinks like Z to the -1/3. If you were at my talk yesterday, I was explaining that atoms do not shrink as Z goes to infinity. And in fact, that's true because the tail behavior of this function is exactly such that these two things cancel. I'll get to that in a minute. The Thomas Fermi potential scales, again, the Z -1/3, and then there's a Z 4/3. And here it is, this function, the phi1 TF, the Thomas Fermi, if its atom was Z equal to 1, behaves like x to the -1 for small x and x to the -4 for large x. So the Thomas Fermi potential, the atom is neutral. So you screen out more and more of the nucleus, and you do not see a 1/x at infinity, you see a 1/x to the 4 at infinity. And notice that the 1/x to the 4 is exactly such that these two things cancel. And you actually have a limiting behavior that is independent of Z at infinity, but also as Z goes to infinity, the whole Thomas Fermi potential converges to this 81 pi squared x to the -4. I know it explicitly. So an infinite atom makes sense. I can take the limit of this as Z goes to infinity, and it converges to, maybe I should write it here because it's so far down. Oops. Oh, yeah. So I'm claiming that phi ZTF converges as a function of x, converges to 81 pi squared x to the -4 is equal to. There's an infinite atom, but notice how bad the singularity is at 0. It's 1/x to the 4. And that means that the whole thing seems rather to be a constant at infinity, and there seems to be no periodicity at all. The whole thing just seems to converge. Well, but that's because this is a little too simple now. Because let me look at the mean field model. For those of you who know density functional theory, there's one step up from density functional theory, which is, I guess, sometimes it's called Hearnshaw theory, where you fill in orbitals instead of just thinking of it in terms of density. So in a sense, that's what I'm doing. I'm saying, let's look at the mean field operator when I take the mean field potential and take the Laplacian. And I say, let me think of this as a model of an atom. So I'm including the interactions in the mean field potential, and I'm filling in the levels in this operator. And again, by the scaling, this operator is unitarily equivalent to something that has a z 4/3, and then the potential when z is 1, and then a z minus 2/3 in front of the Laplacian. And if you think of the way one does semi-classics, there's usually an h bar squared here, and you think of h bar being small. So z minus 2/3 sort of plays a role of an effective Planck constant. And as z goes to infinity, this thing is actually in a semi-classical regime, and you can do a semi-classical analysis of that. But then I can also look at the infinite atom. That's the one where I have 81 pi squared x to the minus 4. Now, well, again, you might say, well, wait a minute, then there is no periodicity. Well, not quite true. There is periodicity, because this operator has such a bad singularity that it does not define an operator. In order to define the operator, I have to tell you, but the boundary condition is at 0 when the singularity is so bad. Here, I don't have to tell you. Here, there's only basically one way of doing it. Well, it's not quite true in the L equals 0 sector, because there are point interactions in 3 dimensions. So, but the operator is bounded from below. There's a distinguished definition. Here, there's nothing distinguished. Here, I have to define the self-adjoint operator. So you may ask the question, if this operator is well defined, that one is not well defined. Is there some way of asking whether that operator converges to this one as z goes to infinity? Okay, what does it mean that operators converge? They're unbounded. Well, you can look at resolvents, and there's something called strong resolvent convergence. Not important exactly if you don't know what it means. There's some way of thinking of a limit of operators. The answer is this thing does not converge, or these operators do not converge as z goes to infinity. What is true, that what we have a whole family, a periodic family of boundary conditions, so that sequences, different sequences of this operator. And I think of these sequences as going down the groups in the periodic. Okay, so I'll get to that, be a little more technical. Well, this is not technical. This, I hope, is just reminding you of how we do an angular momentum decomposition, right? If I have a potential that's radially symmetric and I have an operator, then I can split it in the angular momentum sectors, and I get L times L plus 1 over R squared and the radial variable right there. And I think of these operators here, I call them HL, just in general for something like this. And the HL is an operator acting on the radial variable, L2, I mean, something that depends on the positive real line. Then there we have the angular momentum part. In angular momentum L, it's 2L plus 1 dimensional, and then we have spin. So this is such an operator here. It's defined, and I can think of that operator as being unitarily equivalent to something which is a direct sum. Okay. Now, when I want to understand making such an operator self-adjoint, right, because that's what I mean when I say choosing boundary conditions so that it's a well-defined operator, I want to think of it as a self-adjoint operator. So this is really, it has to do with finding self-adjoint extensions, if there could be more than one self-adjoint realizations. And the self-adjoint realizations of this can be understood by doing self-adjoint realizations of each of the angular momentum sectors. It's not the only way of doing it, but the self-adjoint extensions of A will correspond to self-adjoint extensions of the H else. Slightly tricky because you could imagine having boundary conditions that couple the different L's, but I don't want to do it. I want to have only boundary conditions for each L sector independently. And then if I think of this strong resolvent convergence, I can have convergence by studying it one L at a time. So if I show that if I have a sequence of HNs, and I then do the angular momentum sectors for each of these HNs, and I can show that for each L it converges, then in the strong sense, which is actually not the strongest sense, the strongest sense would be norm resolvent convergence. I'm doing a weaker sense than norm resolvent convergence, which unfortunately is called strong resolvent convergence, but it's weaker than norm resolvent. If you do strong resolvent convergence, then you can study it one angular momentum set at a time. Okay, let me go to the Aufbau principle. I promised I would tell you that the Aufbau principle fails. So here it is. Now, it's a bit tricky because this thing about filling angular momentum, the way we did it in the periodic table, saying that we are filling shells, that's really fake. I mean, there are no angular momentum sectors for a true atom. If I look at the one particle density matrix, gamma psi, you would think that the gamma psi would have eigen that would, if you had the spectral decomposition, you could decompose it into angular momentum sectors. Not true. I mean, first of all, the atom is not spherically symmetric. Right? I mean, we know that that atoms in total may have angular momentum, and there's no reason why a gamma psi should commute with rotations. So we cannot expect that it can be decomposed in angular momentum. So really, the question is not completely well defined. And that's why I put the word number here in quotation marks. I can ask how many electrons do I have in angular momentum L. PL here is the projection onto angular momentum L. If I really had that things would commute, then this number, then would be an integer. This would really count the number in angular momentum L. But it's not true. I don't know that it's a real number. So I should it is a number. It's the trace of PL against gamma psi, but it's not necessarily an integer. But I want to nevertheless study that number because the Aufbau principle told me how to fill in angular momenta. And if I believe it, I can calculate what that number is. There's an explicit formula for that number if I believe in the Aufbau principle. I'm not going to give you the explicit formula. It's a bit complicated. Remember this thing that there were two rows you have to fill up. So if there's something whether even or odd, so the formula is somewhat complicated, but you can try to figure it out yourself. It's a nice little exercise to calculate this NL of psi. But I can calculate it asymptotically, and now you can again not see it down there. But I will write it over here in a moment. I can look at this number when z goes to infinity. Well, when z goes to infinity, it's going to grow. How is it going to grow? Well, that depends on how L is going to grow. But if I now let L grow as z to the 1/3, so the typical angular momentum for an atom of nuclear charge z will grow like z to the 1/3. So I'm introducing a lambda, a number lambda. So lambda times z to the 1/3. And then I take the largest integer bigger than that. And that's L. And now I let z go to infinity. I take the NL psi and I divide it by the degeneracy, 2 times 2L plus 1, and also by z to the 1/3. So this whole thing also goes like z 1/3. So I'm actually saying that this number, if L grows like z 1/3, this number will grow like z 2/3. And that's true also in the Aufbau, if you calculate it in the Aufbau principle. But this limit you can calculate. You can prove what that limit is by using the Scott asymptotics I had. So this really comes from semi-classics. This is what I'm writing over here is really like the semi-classical formula for the number of particles for the one-dimensional open. And I can prove that, well, not quite. It's not a limit, it's a lim inf. I can prove that the lim inf of these numbers, as z goes to infinity, is equal to that integral. Whereas the Aufbau would give me for that number, the Aufbau would for this number here, instead of this quantity, I'm writing it down there, it would give me the very simple formula, 6 to the 1/3 minus 2 lambda. No, lambda was LZ to the 1/3, right? I mean, sorry, Z to the 1/3, L was essentially, Z to the 1/3 lambda was essentially L. If you plug that in to the Aufbau principle and you calculate, you find that that number there is, when you divide by the whole thing by 2, divided by 2L plus 1Z to the 1/3, is this thing, 6 to the 1/3 minus 2 lambda, positive part. So when lambda is too big, it becomes 0. Same thing here. If lambda is too big, this becomes 0. Of course, first I thought, oh, maybe this integral is equal to. But that is not so easy to calculate because this is a solution to some nonlinear equation. But guess who actually had already calculated it? Fermi did. Fermi wrote a paper, Thomas Fermi, when he wrote the Thomas Fermi paper, which is very famous, he wrote 4 papers, they're in Italian. Paper number 2 is asking exactly this question. I had studied Thomas Fermi theory for I don't know how many years. I'd never discovered that there was a paper. I mean, really silly, right? You don't turn to the next page in the journal. Also because I never turned to even the second page because I don't read Italian, right? But there were 4 papers, and the second paper actually suggested that this was the right formula. And then he checked with the periodic table and said, wait a minute, this does not seem to give the right thing for small L and Z. But actually, he was right. If you go to the large limit, this is the right form. And he compared to that. No, sorry, he did not compare. No, he did not know this form, but he calculated it. So you can see this. I don't know how Fermi did this in 1927, right? I mean, maybe he had 100 students that sat there and solved first they had to solve a nonlinear differential equation, and then they had to do a numerical integration. He didn't have a computer, right? I don't know how he did it, but people could do things like that. I believe his result. Well, actually, somebody calculated again now on their PC, and it is true, this is not. So the Aufbau principle is wrong because that is for large, the right, in the asymptotic sense. So there's no way you can give a general proof of the Aufbau principle. Okay, so this was debunking the Aufbau principle. Let me go to this thing about the periodicity. So this was this thing about the self-adjoint extensions of operators that behave really badly at the origin. Remember, I'm fighting this x to the -4. I'll come to it in a moment. Right? I'm fighting a potential. The infinite atoms behaves like x to the -4. So how do I understand this thing about boundary conditions? In fact, when I talked about boundary conditions, this is not quite true because there are no limits at 0. The whole thing is so oscillating, wildly oscillating, that you cannot talk about a boundary condition. You have to talk about the asymptotic oscillating form. So let me explain it to you. So I'm looking at a potential, and you keep in mind x to the -4, or minus x to the -4. And I'm looking at the zero energy equation. So I want to understand this Schrödinger equation. If you try to write down the zero energy, 0 will not be an eigenfunction, so the solution here will not be something that's square integrable, but I can still try to find such a solution. I mean, this is an ordinary differential equation, so it has 2 solutions. And I can study those two solutions. And I'm looking at the case now where both solutions are square integrable near the origin. At infinity, only one of them will be square integrable. But at zero, so there will actually be something that could be square integrable. At zero, there will be something. There will be two solutions that are L2 near the origin. This is the bad case. You might think that many solutions in L2 is good, but that's actually the bad case. That's the case where we do not have a unique self-adjoint realization. A unique self-adjoint, so there's a theory developed by Weil. Weil talks about the limit circle, limit point situation. Limit point means that there's only one solution that's L2 near zero, then your limit point at zero. If you have only one solution in L2 near infinity, then your limit point at infinity. And if your limit point at both ends, well, then there's a unique self-adjoint realization. So I'm looking at the case where we do not have only one solution. We have two solutions, and you should think of them forming a circle, right? I mean, you do this two-dimensional space, but I'm normalizing, and that's why Weil called it the limit circle. So I'm in the limit circle situation. And how do we get the two self-adjoint realizations? Well, you start with functions that are zero near zero. That's what this means. C infinity will compact support near zero. So you start with nice functions that are zero near zero. Then you try to just complete that as much as you can. That's called the minimal operator. So that means that for mathematicians, you're completing it in graph norm. You're taking the closure of the operator. This you can do. You can sort of find what's called a minimal realization, but it's not self-adjoint because this is the thing where you have not yet, it's very small near the origin, so we have not yet specified a boundary condition. And how do you specify the boundary condition? You pick, so if one says that it has deficiency indices 1, 1, so there's sort of a one-dimensional family of self-adjoint extensions. And you choose an F that solves up here, and then you say that you add something, this psi, just something that localizes near zero, so this thing is in L2. And you simply add that to the minimal domain. And the choice of F defines for you a self-adjoint realization. And that's the boundary condition. The F gives you the boundary condition. But when you're in the case x to the minus 4, well, in this case here, what do these F's look like? I mean, the F's that solve this for x to the minus 4, that's explicit. It's x sine something that goes like 1 over x. And then we put it here. So it has the behavior. It's a one-dimensional family, x sine 9 pi over x plus theta, right? And you can choose any theta here. But the difficulty is that it goes like 1 over x. So it goes to 0, but it oscillates like crazy as you go closer and closer to 0. So it's not that you're introducing a boundary condition. I'm telling you that the solutions should oscillate near 0 in a way specified by this phase theta. And by choosing the theta, you're sort of shifting the oscillations, and this will give you different boundaries, different self-adjoint realizations. So that's how you classify it. You classify it. Again, for mathematicians, this domain H-men is really the second Sobolev space, which vanishes near what's called H20. So here's the main result on periodicity. And that is that this periodic realization that I just talked to you about of the infinite atom is actually what you get as possible limits. But there's only one periodic family. You might think that for each angular momentum, that could be a new periodic family, but it's the same one. As you found, when you look at the limits that z goes to infinity, and you look at L equals 0 sector, it will specify for you sort of what its theta should be. And then all the other angular momenta, they're fixed. So this is the theorem. If I look at the Thomas Fermi mean field model, so this is a model for an atom with nuclear charge Zn. I'm asking, when would I have convergence as Zn goes to infinity? And the condition is, you recognize again what we had in that Fermi formula. before, phi 1 to the 1/2. I don't have this minus. Show you. There was a minus lambda squared r minus 2. But now I'm looking at the limit. So now my L is finite. So lambda has to be 0. So I'm looking, then I get the limit without the lambda. I'm claiming that Zn to the 1/3 times a number should converge to something mod 1. So there's a periodicity, there's a t that runs between 0 and 1. And that's because you should really think this is really an approximation to the number of particles in the s electrons in the atom. The number of s electrons in the atom is nearly that with an error that shifted by t. And depending on how much you shift, you get a new atom. Then and only in that case will these converge, and they will converge to the infinite Thomas Fermi atom with a boundary condition at 0 specified that this has to be the asymptotic. But remember that I was talking about this x sine 9 pi over x plus something, right? That's the L equals 0. The one I have up there was for L equal to 0. If I have other L's, the shift depends on L. The phase, the way the oscillations are shifted will depend. But you will have convergence when this converges to a T. You have an infinite atom, and it's described by having this asymptotic. Now, the Aufbau principle would also have this Z to the 1/3. If you don't go down the groups in the periodic table, they also behave like Z 1/3, but this thing would be a 6. That was this 6 from 6 to the 1/3. I mean, sorry, this would be 6 to the 1/3, which it isn't in this model. But here I'm not claiming, I should emphasize, I'm not claiming that I know this for the full quantum model. This I only know in the mean field approximation. I know that the Aufbau principle is wrong for the full quantum model. I do not know how to understand the periodicity in the limit for the full quantum model. This I only know in the mean field. Okay, let me briefly, I hope you have a little more energy. I'll briefly take you through the proof of how you do this. The way you show that there's convergence is basically that you again look at these zero energy solutions. This is the zero energy solution for a finite atom, Zn. If I'm at a finite n, then there's what we call a regular solution. Often there's only one, so for L bigger than or equal to 1, there's only one solution in L2 near the origin to that equation. So you look at solutions to that equation and you want to show that they converge in L2. I mean, when you do square integrability as your norm. So that's what you have to prove. You have to prove that the solutions of this, as z goes to infinity, will converge to these funny integrations that I have, exactly to this function. So you want to show that the zero energy solution near the origin converges to the infinite atom oscillating zero energy solution as z goes to infinity. Okay, so how do we prove this? We do it by WKB. We simply calculate this solution by WKB approximation that we control, and then we show that it will converge. WKB approximation is complicated because we cannot do the standard thing. The standard thing is that you have a classically forbidden region, classically allowed region. You match the two regions by an area, solving an area equation, and you do a match. It's not going to work. The area part doesn't work. So I cannot match. You do not have these turning points when you are in the classical. You do, but that you cannot match at these points because everything is oscillating wildly. So what you do instead is you have classically forbidden regions near zero and near infinity. And you continue these regions into the classically allowed region. You approximate the solutions from the classically forbidden, and you will have oscillations now as you move into the classically allowed for those regions. And then you match those oscillations with the oscillations you get from the WKB approximation in the classically allowed region. And when you are within the classically allowed region, this is called the Green-Liouville or the Liouville-Green approximation. So it looks like this. You have the solution near the origin. This is just hydrogen. This is the zero energy solution of hydrogen that gives you internal Bessel functions. Then you have the classically allowed region, and if you know a little bit of WKB, you may recognize that this is the WKB ansatz. This is a good approximation to the solution in the classically allowed region. And then you study what you get in the classically forbidden region when you are out near infinity, where you have the x to the -4, and then you have this. So these are also two Bessel type. And what you then do is, you know this as a function of z, you match it with that gives you the eta, and then you match it with the linear combination of that as a function of eta, and you end up with the right linear combination of those two. And that's exactly what you're looking for. That was this GL, that's the linear combination near infinity. Now, it may not be so surprising, as I tried to say, that this actually can be done for L equals 0. What is surprising is that it's enough to do it for L equals 0, and then it's automatically true for all other L's. And you get convergence for all. So let me wrap up. So I have tried to convince you that the Aufbau principle fails for large atoms if we do non-relativistic full quantum mechanics. The Aufbau formula is wrong for the number of electrons in the angular momentum L set. I've discussed another model, the Mfield model of atoms, in which I can look at the limit of large Z and I get a periodic behavior. So I have a periodic behavior of the infinite atom, and I know the groups, the convergence in terms of Zn to the 1/3, the different sequences. So I have identified in that model the asymptotic groups in the periodic table. So these limiting sequences produce converging atoms may be interpreted as the groups in the periodic table. I mean, asymptotically, the groups, the columns. And these sequences do not agree with the prediction of the Outbow principle. That's good, because I knew that that was wrong. They do agree with the correct, the one that the Fermi form. So they do agree with that. And of course, the Mfield model that I looked at, this Thomas Fermi Mfield model, is still a simple model of atom. It would be nice to be able to do this in more complicated models. The holy grail is to do it for full quantum description. A slightly less, but still very ambitious goal would be to do it for a Hartree-Fock approximation. And then there's something where you can do Hartree-Fock without the exchange term. I mean, this is more like along the Kohn-Sham theory, where you can do a self-consistent Kohn-Sham where you do not do a semi-classical approximation. So there's sort of a series of more and more complicated models in which you would like to prove this. This is the first step where you know what the atom is, you know the Mfield Thomas Fermi potential, and there we would prove it. So thanks a lot for your attention.
Well, thank you very much for this fascinating view of so imaginative world that has mathematically close connections to our own. Floor is open for questions.
Yeah, I do have a very nice talk, very interesting. But I'm a little bit puzzled. I'm not an expert in Thomas Fermi theory at all, but I was taught that some years ago, and the first thing that they used to tell us is this is not a good theory to describe atoms, and the proof for that is that it does not describe properly the shell structure of atoms, which seems to be related, to me at least, to this Aufbau principle. And I guess this is related to these findings by Fermi and by many other people that have been studying these models. So is there any, but then your work seems to be up to now, at least based on Thomas Fermi. So do you have a clue that in the limit where C goes to infinity, Thomas Fermi should be correct, or at least more correct than it is for smaller systems?
Yes, definitely. It's actually not so bad for a small system. I think so I've tried to promote Thomas Fermi theory.
Okay.
I know that people doing density functional theory. I mean, Thomas Fermi is not going to give you accurate, very accurate ionization energies. I mean, if you're a chemist and you want ionization energies to 2 decimal places, then you may not like Thomas Fermi theory. I think chemists have discarded Thomas Fermi theory way, way too fast. It is true that Thomas Fermi theory does not describe the shell structure of atoms, but this is the Thomas Fermi theory when you just do it as a density function. As soon as I go to this mean field theory, then you do have shell structure. Of course, you may say that that's clear because you are now filling in orbitals in the potential. But what I've proved here is that this Thomas Fermi theory, mean field theory, not only does it have shell structure, it has the correct shell structure for large Z. It gives the correct Aufbau. The Aufbau is wrong if you just do this usual way you are filling up. If we continue the usual way we're filling up we know to fill up the periodic table, we would get a wrong answer for large. So Thomas Fermi would be good for large Z. But of course, it's a relevant question. How good is it for small z if you really would like to? I mean, would it make sense at all to do things with Thomas Fermi? So some years ago, this is this thing about the size of atoms. Can we use Thomas Fermi theory actually for finite z? So I realized that it was not so good for ionization. But for the alkali atoms, let me go back. I actually I actually do have the graph on my. Maybe I should show you the graph. Well, okay. Right, I want to go to. Right, so for the alkali, the group 1, I actually try to calculate the radius of the atom. So what radius of an atom is not entirely well defined, right? Because the wave function spreads out everywhere. And what do we mean by the radius? But there is this radius that Bjerg, Slater, Pauling, where you do simply half the distance in diatomic molecules, right? Or half the distance in other compounds, right? So if you look at the chemical compound and you look at some atom, say sodium, and you look at the binding distance to another molecule, to another atom in a molecule, it turns out that you can associate a number to each atom in the periodic table so that the distances in molecular bindings is essentially the sum of the numbers, right? So they're really like atoms that are stuck next to each other. So I tried to see if I could calculate with Thomas Fermi theory that radius. So what did I do in Thomas Fermi theory? I said, let me take Thomas Fermi theory for the alkali atoms. And I know the alkali have 1 extra electron, right? It's a noble gas where you add an extra electron. So I tried to ask, where is this last electron? So let me go out to the radius so that there's 1 electron outside. And actually, it's numerically accurate for the radii of these. I mean, there's some of them, I think potassium, it gets arrived to 1, I mean, less than 1% compared with some of the calculations that Slater did. So Thomas Fermi theory is surprisingly good. I also tried to use Thomas Fermi theory to calculate repulsion between, I mean, when you try to squeeze atoms together, they will start repelling because of the Pauli principle. So I tried to calculate this repulsion. And Thomas Fermi theory, one of the big problems is that it cannot bind. It will never predict binding. So this is Teller's theorem that says there's no binding in Thomas Fermi theory. And that's of course really not good if you want to, but you have to use it where it's supposed to be good. It's supposed to be good if you go a little bit beyond binding and try to calculate the repulsion. So I tried to calculate the repulsion for lots of diatomic molecules, and I compared with Hartree-Fock calculations. There's this Dalton program that done by chemists. There's this consortium called the Dalton brothers, I guess they call themselves, that has this program where they can calculate Hartree-Fock theory. And I asked them, can you calculate this repulsion for me? And then they said, no, because our program is not made up to have short distances beyond the binding distance. But luckily, they were fascinated by the question to ask, I mean, every time you try to challenge the method in some way, they say, okay, maybe can we adopt it? So they actually redid the code to calculate the repulsion at short distances. And we checked it, and Thomas Fermi theory is spot on when you do a fairly low distance. So I wrote a paper in molecular physics where I tried to say, try to look at Thomas Fermi theory one more time. Maybe it's much better than its reputation. And at least it's fundamental. You can derive it. Many of the other density functional theories are completely phenomenological. You should take it for what it is. It's definitely good for large Z. It's surprisingly accurate if you stick to the right question, also for small Z.
Anyway, well, just very short comment. But I think you are right, Mark, that including exchange is very important for this problem. I fully agree with that. I think that particularly when you look at the behavior nearby the origin, this has to be crucial. But there are extensions with this, for example, the von-Weizsäcker functional for the kinetic energy, where you can include that. And maybe, I mean, it's not easy to treat those terms for sure, but
actually, it's not so difficult. I mean, so if you give me a density functional theory, much of this will actually go through. The problem is that it would be some work every time you give me a new density function. And so mathematically, it will not really be all that different, depending on a little bit what type of exchange correlation. But say if you just add a Dirac term, which is the rho to the 4/3 as your exchange correlation, then it should not be a big problem to repeat some of these arguments. But yes, I mean, of course, the exchange correlations will be important. You will not have binding without them. Thomas Fermi theory itself will not have any binding. So if I want to estimate the binding distance, I cannot do it with pure Thomas Fermi theory. I think I can do it with the mean field Thomas Fermi theory, actually, but that's a difference.
thank you.
Yes, well, you are concerned with atoms, but also we have systems with plenty of electrons that are considered like superatoms, like big helium atoms with helium models with a lot of electrons and so on. Do you think this some of these conclusions about the above thing, how they could be applied there also? Or
These are still atomic structures?
Like a helium cluster with many atoms and many electrons and so on. These above things will also be there, or these problems?
Some things will still be there. I don't know in that case what I would be able to show mathematically, but yes, I mean, I have also studied molecules, and here I only talked about
no molecules. Just thinking that you have like a helium model with many electrons to deal like I don't know, 10,000 sodium atoms.
But they will still have it. The nuclei will still have some distance from each other.
Levels, but how they go? They will still fill with.
Yes, but you may ask whether this would be a good model for me because it has large number of electrons.
Yes,
but that's not entirely true because there will still be a distance between the different helium nuclei, and that distance will be on a scale where they will actually where my analysis might actually fail. So if you try to do it for clusters of atoms, it has a lot to do with how your cluster scales. So it's very, it would, in principle, I should be able to do it, but I don't quite know how to treat the distance between the helium nuclei for such a thing. I would have to go to a model that had binding, so I would know where they are. And such models are just, for the moment, they're too difficult for me to treat.
Yes, I have a question somehow related to the one that I will ask you, and it's about what you have said that the Aufbau principle doesn't work for large atoms, and it is true, but it is also true that at least for the periodic table, it works, and those are the atoms that we have.
Right.
And the reasons why the Outbow principle works in the periodic table, I think are understood, right? It's just
I don't think so.
The nature of the potential, of the nuclear potential, and the fact that when you fill shells, the electrons have to be orthogonal to the ones of the shells before. I think that explains through the Schrödinger equation the formation of shells. On the other hand, what those two pieces, potential, singular potential of the Coulombic of the nucleus, and the orthogonality are the two main ingredients. But in other systems, for instance, in nuclei or clusters, like you say, the potential is different. It's not a singular potential. It's a potential more like, well, there are no nucleus inside the nucleus, right? So it's a not singular potential, and the potential is created by the particles themselves, like in a quantum dot or in a nucleus. And then the potential is, say, something in between, close to a step potential, a simple wall potential. So, and that, because the potential is different, the Aufbau principle, if you want to call it in that way, or the way in which the shells are filled in nucleus is different from the way in which they are filled in atoms.
Yeah, so I wouldn't quite know how to study nuclei because I don't have, I would have to pick the model first. I cannot go all the way to quantum chromodynamics. I would have to choose some mean field model. So I don't know how to do this, but let me go back to what you're saying about for finite Z, where we understand it. So I agree with you, we understand it because we can calculate the structure of those atoms to a certain approximation, or we can measure, right? We can even measure there's been a lot of discussion about Laurentium actually, right? Is it in the right place when you use the Aufbau principle? And it turns out it's not, but people say that's because of relativistic effects. So we can both measure and try to calculate. But if you by understand mean that we have a simple explanation which does not require us to calculate every single atom. You're saying a simple explanation that you are filling orbitals and they are orthogonal to each other and so on. That argument should work no matter how large an atom I choose. And it will not give the Aufbau principle. That's what I say. If you just use such a simple argument, it will not give you Aufbau. It will fail when Z becomes large. And another thing is that it doesn't even make sense to talk about orbitals. I know we are so ingrained in us that we talk about filling in electrons in orbitals. But what is an electric orbital? Well, chemists also know this, that we have natural orbitals. The natural orbitals are the eigenfunctions of the one-particle density matrix. They are not given by angular momentum. I know that we often give them by angular momentum. That's an approximation. It's not true in general. So there is really no way of talking about orbitals and labeling them by angular momentum. That in itself is an approximation. So mathematically, there's just no way you can actually prove the Aufbau principle or explain it and say that we understand it. I do think that the model I look at will give the Aufbau if I do it for small z. I was doing the asymptotic case to say that it will not give the same structure if you keep going. So this rule that we have for filling in has to fail at something. So if it's true, it's by coincidence for small, that it just numerically happens to be that you can approximate it by that rule for small z. And I think even the model I look at, this Thomas Fermi model, will actually do this. I haven't done this computation, and I'm surprised that it was never done. Fermi didn't do it because I guess he did not have enough students to do their calculations. So he did only an asymptotic calculation. But I think I'm hopeful. I have a student working on it now to actually see if you reproduce Aufbau by this simple mean field Thomas Fermi model. And I have hope that to some extent you do. But saying that you understand it, I would actually disagree, because the understanding at least would fail, has to fail somewhere. So you would have to explain to me why it's not just a numerical calculation, and what do we then otherwise mean by an understanding?
So you mentioned in your talk that you use a non-relativistic approach for yes. So let's forget about a full relativistic approach, but let's consider the standard fine structure perturbation that we can go to the standard classical approach. Which one of the terms will be more critical for your approach?
Well, the
limit of large C.
So I can actually try to do a relativistic approach. The difficulty, so to make some mathematical statements, I wanted Z to go to infinity. That will create instability no matter what. If you do a fine structure perturbation, or if you look at the Dirac equation and try to solve it completely, when Z times the fine structure constant becomes 1, well, then the atom, you still have an atom, but as soon as Z times alpha is bigger than 1, it becomes unstable. I mean, the gap, the eigenstates in the gap will start falling into the continuum, and you cannot study it. Now, there's still one way you could get around that. And that is, but that's sort of, again, like a mathematical trick to be able to study it, to say, let me not only look at large Z, let me at the same time think of the fine structure constant getting smaller and smaller. So if you allow me to change the fine structure constant as I increase Z, so that I limit, and I think that is actually okay to understand it. It will understand some relativistic corrections, those that are of order Z times alpha. So you have corrections, you have relativistic corrections that are of order Z alpha. And if you keep Z going to infinity, alpha going to 0, so that Z alpha is a constant, then I can study those corrections, and everything would work. Because you can do what I call the Scott expansion. This thing here, the 1/4 will start depending on the fine structure constant. It will depend, it will become a function of Z times alpha. And if Z alpha gets bigger than 1, it's hopeless. It becomes minus infinity. But if you keep Z alpha fixed less than 1, as Z goes to infinity, alpha goes to 0, then you still have that expansion, and you can still study, and everything will still go through, and you will get the same rule for the alpha.
But this would not also affect your boundary condition, because at some point you are assuming that the L subspace are not talking to each other.
Yes. So I make it sound easier than it is. You would have to study the Dirac equation and the oscillations that come from the zero energy solutions of a Dirac equation. So you would have to match, instead of matching the zero energy solution for hydrogen. So this was this. So I haven't done it. I'm just saying I am confident that it would work. Instead of matching, so this is the zero energy solution in angular momentum alpha hydrogen. You would have to do the corresponding thing for the Dirac equation. I think it's also known explicitly in that case. I mean, it is known explicitly, but I don't know how complicated it is. And then as you go into this region, then you can already forget relativistic. The relativistic corrections are the innermost electrons, those that move really fast. So here, even when you do sort of an approximation, you would be able to study this. The problem is that I'm lying a little bit, because we don't know how to treat the Dirac. I mean, what exactly do we mean? How do we fill the Dirac C? What type of approximation do we? I don't really know. We don't have a fully relativistic theory. So I would have to do some approximation to a relativistic theory. But in some of these approximations, they're all different kinds, where you project out the vacuum, you freeze the vacuum into the free vacuum. So there are all these different ways you could try to do it. And I think in all those caricatures of a relativistic theory, I would be able to do the analysis. And I think they would probably reproduce at least the fine structure behavior, but they would not be fully relative.
Okay, so let's thank Mr. Solovej for it.
No, a mí me liaron. Antes me recuerda a Elliot Lee, que cuando nos explicaba aquí Elliot Lee. Pues hace muchos años, pero yo le llevé a la prueba de Hain, etcétera. Cada 20 años que se casaba con la misma mujer.
La misma 20 años más joven.
Sorry,
Bueno, voy a decir que de acuerdo también.
I thought it was
Hello. I was a good friend and he came here many years ago, Philip Solovej. That
Yeah.
remind me of him.
He was my PhD advisor.
How is he?
Actually, quite well. So he's
Do you see him or correspond with him?
yes, of course. So we Zoom.
Send him my regards.
I will.
Pedro Echenique is my name.
Okay, I will.
He came,
Yes.
he was very interested in addition to physics to some caves that are the Basque cave of
Yes.
a kind.
He loves to travel.
And I went, he's an obsessor of the timing. I had to pick him up in Santander, and until I arrived to the room, he was not.
And this was many years ago, right? Now you should imagine
No, even
today
more.
when he's 91 years old. He does not like to travel unless somebody
Yeah,
is with
but
him all the time.
when I appeared in the room in Santander, he said, because he knew
I
the
know exactly what you're talking
same
about.
timetable that, and I very good friend, he came here many times, Phil Anderson. And
Yeah, okay, right. Sometimes they clashed. That's right.
each other thought of the other. They were too clever for the stupid things he was doing.
Exactly. Yeah, you got it. That's exactly right.
So
They still had this sort of humoristic way of.
Phil has died.
Yeah, Phil has done. But
Send him my regards.
I will.
to
So
the-
he's 91 years old. He wants to travel to Mongolia with his wife. He tried last year, and then for some reason the thing was delayed by 4 days, and then he gave up. He didn't want to wait 4 days.
Has to know by the minute.
Exactly. So 4 days for him was hopeless. But he has not given up going to Mongolia. I will. Thanks.
I also enjoyed, the paper that you mentioned that had so many quotations, right? That it was,
Or the Bjerg
yeah, it was-
in the
yeah, but it was led by Lucien Constantin.